Science is founded on practical work. The phrase scientific experiment encompasses a vast range of activities. Here at CERN, the European Organisation for Nuclear Research, multinational teams with annual budgets of millions of pounds devise experiments to probe the ultimate structure of matter. This equipment monitors subatomic particles that may only exist for billionths of a second. In complete contrast, in some scientific research, the work consists mainly of qualitative observations in the field, often carried out by just one person. For example, the investigation of these folded strata near the Lake District begins by noting the kinds of rock present and their inclination due to the folding. It does take time, but it doesn't need any elaborate equipment. Behavioural studies, too, are largely a matter of observation, although quantitative measurement may come in at a later stage. These fish have been conditioned to swim towards the light in the expectation of being rewarded with food. In this programme, we're going to consider 4 experiments. They're all quantitative, but otherwise they're quite different in subject and in character. 2 are fairly rough and ready, 2 rather more sophisticated. But they're all indisputably scientific. While you're watching, see if you can pinpoint what it is that characterises them as scientific. Do they have any common features? We'll begin with an experiment you've already done yourself.
It wasn't so long ago that you were hoping for the clouds to clear so that you could do an experiment of your own. The aim of the experiment was to determine the distance to the moon by the so-called eclipse method. When I did the experiment, I used a broomstick and one of the discs from the experiment kit. The wire around the stick and the back of the chair gave some sort of flexible support. I sellotaped a tape measure to the broomstick to make the measurements as quickly as possible. Well, I haven't got a moon to show you today, but I'll use the clock up there. We encourage you to practice with other objects if the moon was unavailable. On the night I made my measurements, the moon was almost full. Unfortunately, it was cloudy, and I could only see the moon intermittently. I see from my lab notebook that I made 3 separate measurements of the eclipse position. That's the eye to disk distance. In 2 of these, I got estimates for the maximum and minimum eclipse positions. In the 3rd case, the moon disappeared too quickly, and I was only able to obtain 1 reading. I got a result for the Earth to moon distance eventually. When I came to analyze the uncertainties in my measurements, I found large uncertainties in my value for the eye to disk distance and the radius of the moon that I determined using the photographs in the text of Unit 2. I couldn't do much about the photographs in the text, but the uncertainty in the eye to disk distance could have been reduced using a longer stick and a larger disk. One of my students was 1 step ahead of me with this conclusion. He's in the fire brigade, and he used a very different set of apparatus to mine. Note the important refinements. His broomstick is much more stable and steady compared to mine. It's easier to work with. Furthermore, the eye to disk distance is very much larger, and so the uncertainty in this measurement is much smaller. In fact, my student didn't use a disc of fixed diameter. He got one of his colleagues at the top of the ladder to define the edges of a disc with sticks. Then, by varying the distance apart of these sticks, he could decide on a range of values for the disc-like diameter that eclipsed the moon. So, he kept his eye to disk distance fixed. It was the length of the ladder, and he varied the diameter of his disc. It's just as valid a way to do the measurement. And of course, the diameter of his disc was large. And so again, the uncertainty in this measurement was much less than in mine.
Incidentally, you may have noticed that because of the constraints of the drill yard, the firemen didn't position the ladder square onto the clock face. Now, if they'd really tried to measure the diameter of the clock face, this would have introduced a sizable systematic error. Of course, this problem doesn't arise if you're eclipsing a spherical object, like the moon. Well, we'll stick with matters astronomical for the next experiment too. But this one illustrates a different sort of process. the testing of a new theory. This is quite a common role for scientific experiments, and usually the sequence of events goes something like this. Somebody dreams up a theory, and the theory is then used to make a prediction. Finally, an experiment's devised to find out whether the predicted behaviour is observed in practice. Of course, one has to be a bit careful, because even a positive result doesn't prove that the theory is correct, although it certainly does give it a boost. A good example of this sort of process is the search for a theory of gravitation. As you know, Newton had a pretty good theory, so good that it kept scientists happy for 250 years. But that all changed in 1916, when Albert Einstein put forward a completely new description of gravitation, his general theory of relativity. Now, when gravitational effects are fairly weak, as they are around the Earth, Einstein's theory makes exactly the same prediction as Newton's. The two theories only diverge when considering the gravitational effects of truly massive objects, such as the Sun. Now, you know that according to the ideas of general relativity, light from the stars will actually show some gravitational deflection when it passes close to the Sun. So if we look at a star that's close to the Sun, Einstein's theory would predict that the light from that star would have travelled in a curved path to reach us. But because we tend to think that light always travels in a straight line, we would actually say that the star was here. In other words, from our viewpoint, the star would apparently have moved because of the presence of the Sun between it and the Earth. The effect's exaggerated here. Really, the shift is extremely small. And there's a practical problem about observing it, which is that when you look towards the Sun, you can't usually see the stars because the sky's too bright. So what's needed is something that will block out the light reaching us from the Sun. And that something needs to be outside the Earth's atmosphere if it's to have any overall effect in darkening the sky. The one object that will do this job perfectly is the Moon. When the Sun's disk is totally eclipsed by the Moon, the stars can actually become visible in the middle of the day. So the historic experiment to test Einstein's theory boiled down to observing and recording on a photograph the positions of known stars around the edge of the Sun's disk during a total eclipse. Remember, two teams of scientists set off from Madeira to make the measurements. One team, led by Sir Arthur Eddington, went to the island of Principe, here, and the other team to Sobral in Brazil. So why two expeditions, and why to such relatively remote places? Well, solar eclipses are fairly rare events. At most there are 5 in a year, frequently fewer. And each one will only be observable from a few places on the Earth's surface. During the 1919 eclipse, the Moon's shadow passed over this part of the Earth. Principe, Brazil. In each place there was just the one opportunity to make the measurements. And of course, the trouble with an experiment that you can only do once is that it's very vulnerable to systematic error. Eddington's telescope and camera had been checked and double-checked beforehand, but even so, some fault might have crept in on the very day of the eclipse. Without the other group's data to compare his results with, he would have had no way of testing for systematic errors in his instrumentation. Well, as you know, it did all work out fine on the day, despite an overcast start in Principe, which must nearly have driven Eddington to despair. His photos not only showed that the stars appeared to move outwards due to the presence of the Sun, their apparent displacement was of exactly the magnitude that Einstein had predicted. Principe experiment was a triumph for general relativity. Einstein, by the way, wasn't surprised. He once said that his theory was too elegant to be false. Eddington's experiment, designed to test a new theory, was one of the classic experiments of the 20th century. For our next experiment, we'll go back to the 19th century and the work of Lord Rayleigh on the density of gases. This turned out to be something of a detective story, because he got rather unexpected results, and these in turn led to an important new discovery.
Lord Rayleigh was interested in making accurate measurements of the density of gases from the atmosphere and from various chemical sources. The atmosphere consists mainly of oxygen and nitrogen. In fact, until 1894, it was thought that the only other constituents of air were carbon dioxide and a dash of water vapour. Let's look at some of the results Lord Rayleigh obtained for the density of oxygen from different sources. Note the experimental uncertainty in each of the results is the same. It's plus or minus 0.0001. Look at one set of data for oxygen. The uncertainty in the measurement means that the last figure in the density ticks up or down by 1. Only the last figure changes, and that's all. I think you'll agree it was a precise measurement. And moreover, allowing for the uncertainty, all the results are the same. Now, a similar exercise with nitrogen gave Lord Rayleigh some very surprising results. Let's look at the data. We are still measuring density, so the uncertainty in the measurement remains the same. It's the same kind of measurement on a different gas. However, look at the difference in the density of nitrogen from the two sources. The difference is 0.0061. That's 61 on a scale where we only expect a difference of 1 from the uncertainty. And doing the experiments time and time again gave the same results. Eventually, in September 1892, Lord Rayleigh wrote to Nature.
I am much puzzled by some recent results on the density of nitrogen, and shall be obliged if any of your chemical readers can offer any suggestion as to the cause. According to two different methods, I obtain quite distinct values. The difference is small in itself, but it lies outside the errors of experiment, and can only be attributed to a variation in the character of the gas.
Enter Sir William Ramsay, who in 1894, working in collaboration with Rayleigh, showed that nitrogen from the air contained a small amount of what he called unreactive gas. Let's model our air like this. He was careful to remove oxygen and carbon dioxide. He dried the gas and even removed any dust that might be present. Here's a picture of the apparatus he used in his lab notebook. The idea was to pass the nitrogen over the red-hot magnesium to see if it would be completely absorbed. If it was only nitrogen, it should have been. But when he did this experiment, a residue of gas, about 1/80th of the original volume, always remained. We can get a clear account of this work from a letter which Ramsay wrote in August 1894 to his Aunt Louisa while he was on holiday on Arran.
Have you seen a notice of the new gas in air, of which Lord Rayleigh and I gave an account? I asked him if he minded us trying to solve the mystery. He thought that the cause of the discrepancy was a light gas in non-atmospheric nitrogen. He spent the summer in looking for the light gas. I spent July in hunting for the heavy one, and I have succeeded in isolating it.
This new element was called argon, from the Greek meaning the lazy one. It was well named, since this colourless, odourless gas with a high density is extremely reluctant to do anything but be itself. William Ramsay went on to discover other lazy gases. Helium, a gas that is present in the sun. Neon, which gives the red colour to neon lighting. Krypton and xenon. All these substances became known as the inert gases. But it all began with the accurate and careful measurement of the density of nitrogen by Lord Rayleigh.
Ramsay and Rayleigh had an unexpected result to explain, but at least they had a very clear idea of what they were measuring. However, there are occasions when it's not at all obvious what quantity should be measured. For example, suppose we wanted to assess the fitness of those runners. What factors would we have to take into account? The trouble is that fitness is a rather vague term, We've all got an idea of what it means, but how do we go about attaching some sort of reproducible numerical value to it? This is one of the things they're working on in the Department of Sports Science at Loughborough University. Actually, no one has yet come up with a reproducible, quantitative method of measuring fitness. Still, the story of the search for such a method highlights one of the most important problems associated with experiments in biology. You can immediately see what this problem is if you think for a moment about an event like the London Marathon. In 1986, this was won by the Japanese runner Seiko in a time of about 2 hours and 10 minutes. Runners in the middle of the pack took between 2.5 and 3.5 hours to complete the course. Older runners, perhaps as long as 5 or 6 hours. In a sense, all these people are fit. After all, they can all run 26 miles. Yet even among the marathon entrants, there's a vast spread in performance. And that's always the problem about any kind of study of people. There's a natural variation between individuals within the sample. Here at Loughborough, they mostly use their own students as guinea pigs, so that helps to narrow the sample down a bit. Students are all roughly the same age, and they're all here because of their outstanding ability at some sport or other. So in comparison with the general population, they are all fit. But how fit? First of all, let's limit ourselves to thinking about what's called endurance fitness. That's the sort of physical stamina that enables people to complete a marathon. We won't actually make our test group here run the whole marathon distance, but we will ask them to run a fair way, let's say 5 kilometres, and record the time each one of them takes. Right, now we've got everybody's time over 5 kilometres. But what does that tell us, apart from the fact that some people run more quickly than others? What we want to do now is to compare these results with some other objective method of assessing fitness. One of the simplest of these methods involves measuring a person's maximum uptake of oxygen during exercise. The reasoning behind this is quite straightforward. The level of physical activity Sonia can maintain on this rolling road is governed by the amount of air she can draw into her lungs and by the amount of oxygen she can get out of that air to make the necessary fuel for her muscles. And the rate of extraction of oxygen is in turn related to the efficiency with which her heart pumps blood around her body. These sorts of measurements are a matter of everyday routine for Professor Williams and his colleagues at Loughborough.
We would collect the expired air for a minute, and then we know, for example, that the oxygen content of the external environment is about 20.9%. And then we analyze the contents of the bag for oxygen and carbon dioxide, and from the subtraction between the known quantity of oxygen in the external environment and the quantity in the bag, we can find out how much oxygen has been extracted by the person during the run.
So what they're determining in this part of the experiment is a rate of absorption of oxygen, a volume per unit time, units centimetres cubed per second. And then they do one other very important thing, which is to weigh the person and to divide the oxygen absorption rate by their mass. Obviously, a very large person will require more oxygen to fuel their muscles than a very small person. And you don't want differences in fitness to be obscured by simple differences in physical size. This kind of procedure is quite a common scientific technique. It's called normalization. Now, along the horizontal axis, we've plotted the time taken to run the 5-kilometre distance. Each point refers to one individual. For example, the filled-in circles correspond to the men in the sample and the open circles to the women. Professor Williams has found that for any one individual, the results of experiments like this are reproducible to within quite a small uncertainty. Now, this is a rather different sort of graph to the ones you've seen so far in the course. The axes don't represent independent and dependent variables. It's not a question of varying one quantity and seeing how something else changes as a result. What's been done here is to plot two different types of information against each other to see whether there is any correlation between them, which clearly there is. The points aren't randomly spread all over the graph, so there's obviously some connection between these two quantities. And broadly speaking, it seems that the lower your maximum oxygen uptake, the longer you will take to run the 5-kilometre distance. And it's also interesting that many of the women seem to fall in this part of the graph, while the majority of the men are in this portion. But there's obviously quite a lot of overlap in this middle region. So let's look a bit more closely at the differences between the men and the women. Starting from these data, I can produce yet another different type of graph. Along this axis, I'll again plot the time for the 5-kilometre distance. But this time, up here, I'm going to plot the number of individuals who can complete the distance in the given time. So, for example, only 3 men covered the 5 kilometres in between 14 and 16 minutes. Whereas 11 men could manage it in between 16 and 18 minutes. Well, I'm not going to transfer all the data now, and anyway, this sample may not be quite large enough to demonstrate the point convincingly. But if I were to carry on building up the histogram in this way, I'd eventually get a curve something like this for the men. And if I then worked out the results for the women, I'd get a similar shaped curve, but displaced a bit, because on average the women take longer than the men to cover the 5-kilometre distance. These sorts of graphs are called distribution curves and are used a lot in biology. In fact, you'll draw some for yourself at summer school. And what these curves demonstrate is that you have to be very careful in biological experiments to make your measurements on a representative sample. If I'd looked only at a couple of women who'd happened to fall in this region, and a couple of men who happened to fall on this part of the male distribution curve, then I might have concluded that women run more quickly than men, which is exactly the opposite of what actually happens on average. For conclusions from this sort of experiment to be valid, you have to be sure that you've encompassed the full range of natural variation. So the biology experiment differs in 2 main ways from the physics and chemistry experiments we looked at earlier. First, because there is as yet no detailed quantitative theory to fit the results. And second, because of this problem of the variation between individuals within the sample. At the beginning of the programme, I suggested you might like to see whether you could spot any features common to all the experiments. Actually, that's pretty hard to do. Certainly you might have noticed things like having a set of carefully controlled conditions, keeping records of observations and results, or trying to assess and minimise the uncertainties. But even there, the approaches varied pretty widely. You will also be doing a whole range of practical work in the course, from measuring the number of atoms that combine to form a particular type of molecule, to investigating past life on Earth using fossil casts. The first of these is quantitative, the second purely observational. They're very different types of experiment, but both perfectly valid forms of scientific inquiry.